Hi, everybody. In this talk, we will discuss the postulates of quantum mechanics. But before some preliminaries, I must say that quantum mechanics started with Planck around this year when he postulated the quantum to explain black body radiation. And in 1924 or around that year, Louis de Broglie postulated the wave particle duality, which means that based on some ideas that light behaves as particles and waves in distinct situations, they really thought thought that maybe massive particles such as electrons would behave as waves in some situations and as particles in other situations. And that was promptly demonstrated experimentally by Davidson, Germer, and Thomson. This Thomson here was the son of J. Thomson, which discovered the electron and as a particle, and his son, this Thomson, discovered that electrons behave as waves in some scenarios. So, what Planck really proposed? Okay, Planck energy is related to angular frequency. This h bar is Planck's constant divided by 2 pi. So in the international system of units, it corresponds to around 1.055 times 10 to the minus 34 joules seconds. Okay, this is Planck's constant. Planck proposed this relation. Energy is related to a wave characteristic, which is frequency, angular frequency. And de Broglie proposed that the momentum, modulus of the momentum, is equal to Planck's constant divided by the wavelength. Or you can reverse the orders here. The wavelength can be calculated from momentum of a particle. For massive particles, this is the mass multiplied by the velocity. But in general, as for photons, you have a wavelength and photons don't have mass. So even this way, even in this case, you can calculate the momentum. If you multiply and divide by 2 pi here, this equation, 2 pi over 2 pi, notice that this is the h bar constant, and 2 pi over lambda, this is the wave number, h bar k. So since wave momentum is a vector, this can be related directly to the wave vector whose modulus is the wave number. Okay, so this relation can be generalized. Momentum is equal to h bar multiplied by the wave vector. Okay, so there are relations between wave characteristics and energy and momentum, which normally we assign to particles. So these are the preliminaries. I must remember you that a function of spacetime which carries all this information a specific energy and momentum value uh, corresponds to a plane wave. So, if you remember, a plane wave has this mathematical structure. It is a complex constant multiplied by I to the exponential of minus I omega t minus k dot position r. Okay, this is non-localized in time. It exists from minus infinity to infinity, and it's non-localized in space. A plane wave exists over the entire space. So, anticipating some aspects of quantum mechanics, if you would to interpret this as a probabilistic function, notice that the probability of a particle to be in any specific place is equal to any other place. So complete delocalization. You don't have any certainty about the position or the instant of time that particle emerged. So you have no knowledge about position and instant of time, but you have complete knowledge because you know the frequency exactly and the wave number exactly. You know exactly the energy and the momentum. So you don't have any uncertainty in energy and momentum, and you have a complete uncertainty in position, for instance. Okay, you can translate the omega here as the energy divided by h bar. It multiplies time t, and the k there you can replace using de Broglie relation by momentum scalar product with position. Remember that the scalar product of these two objects gives you a k of x multiplied by x times x, ky times y plus kz times z. So this is an exponential depending on space and time variables, but with a specific energy and momentum. So you can take the Fourier transform of this function to go to space of omega and k, and you'll find a Dirac delta. Suppose energy is 0, p0 here, omega 0, k0, you'll find Dirac deltas. You can work out these calculations, okay? Also, you can, as an exercise, calculate some numbers. For instance, a electron, 10 electron volts of energy, you can determine frequency and wavelength and all that the properties. I'll leave you to you do the math. So 10 electron volts, you can calculate the angular frequency associated with this energy and the wavelength. You can eventually notice that this order of magnitude for electrons, non-relativistic electrons, is the Fermi level of some metals, some materials. And you can calculate for a photon. Okay, if you pick up photon with say 10 kilo electron volts, it is a X-ray photon, highly energetic. It is uh, 3 orders of magnitude more energetic than this electron. you can also calculate the omega of this photon and the wavelength of this photon. But remember, here the energy relates to the momentum by p squared over twice the mass of that electron. And here you have the energy is equal to the speed of light multiplying the momentum. So you can use de Broglie relations. Here, you remember P is equal to h bar k. Here also, and energy is equal to h bar omega. And you can calculate these things. Okay. So far, so good. I will not extend this discussion because we will. I hope we will touch these points again. But also, you can determine in a simple calculation for the function what does that mean to take the time derivative and to take partial derivatives. You'll see here you obtain minus e omega, and here for that function psi is equal to psi 0 subindex 0, it's a constant here, I to the exponential to the minus I omega t minus k dot r. You'll see that applying the time derivative, it's like replacing the derivative by minus e omega, and taking partial derivatives, it corresponds to multiplying by the imaginary unit k and repeat the function. So you can show that. I will not show that, but it's easy. Just apply the operators here. You'll find derivative of this function gives minus I omega repeat function. Nabla or applied to this function will give you I, the wave vector k, and repeat the function. So you can do the math. Okay. So let's start with the postulates of quantum mechanics now. Proper postulates. Postulates of quantum mechanics. Okay. In that problem of calculating wavelengths and angular frequencies and related to energy and all that, you can think a little bit about what are the meaning of a photon momentum and what relation does it have with the energy of a photon and all that. But as I said, we will discuss that a little longer, I hope, in the future. So, first postulate, the first one, it's very important, okay? Hilbert space, which we already discussed previously. The physical system, any physical system, your physical system can be an electron or a bunch of electrons or a photon or whatever. And a physical system must be described. Maybe you can find better words than that I'm finding now, but any physical system must be described by a ket or a brow, of course, a ket psi in Hilbert space. Okay, so the physical system, the state of the physical system is this thing here, all right? The state defining in what condition is your physical system is this object. It is a vector in Hilbert space. All right. In quantum mechanics, physical system is represented by this object. I can contrast to what you find in classical physics. Okay, in classical physics. For instance, you pick up in a classical electron. Okay, so you'll describe your classical electron by position and momentum. These are functions. You don't need to discuss in a profound sense what is this thing and that one, because these are trivial functions in the sense that they are mathematical functions of time, x of t, y of t, and z of t, and so on. But in quantum mechanics, quantum world, say, the electron must be represented by a function, a ket, a vector, better said, a vector in Hilbert space. This is the physical state of the electron. But and for these things must be. I will not use these brackets here because it may be resembling a commutator, which we'll find later. So just the comma here is enough. What do you need to do with these things? The physical observables, which in classical physics, in classical mechanics, we observe the position and the velocity of the electron. Supposedly, we do not interact in a destructive manner. We do not interact when measuring, or ideally, we do not affect the state of the electron when measuring classically. So, what can I do in quantum mechanics? Well, these things will be replaced by operators. Okay, the position operator, do not confuse with a unitary vector, a unit vector. This symbol here, this hat here, just denote an operator. Okay, and momentum also will be described by an operator, a vector. And what I can say about the electron, I can say I can find perhaps average over the physical state of this operator. I will have an average, a possibility in average of finding an electron at a given position. In average, you will find something, a numerical value, but I must calculate things like this. All right. So in a quantum world, the fundamental object is this here, the ket, the state in the Hilbert space. In quantum mechanics, everything occurs, the arena for the events is the Hilbert space, not what we see macroscopically speaking, in usual sense of classical world, in macroscopic world. In quantum mechanics, things happen in the Hilbert space, which is a complex, abstract vector space. And electrons, or whatever, are represented by a vector in Hilbert space. And the dynamics of the system must be represented there. It's in the Hilbert space where dynamics unfolds, okay? And what can I expect for the macroscopic world or for measurement? I can expect probabilities, okay? I can only expect probabilities, all right? So let's talk a little bit more about this important information. Um, a physical state psi can be expanded in a given basis. Suppose it is discrete, but it really can be continuous, right? And this object is expanded in terms of a given basis in the Hilbert space. These vectors are allowed states for the physical system in that basis, okay? And this can be a linear superposition of states in that basis, all right? I can expect that the amplitudes or the complex amplitudes here are functions of time. So we'll talk about the dynamics later. So in Hilbert space, you have the state 1, state number 2, or alpha state here, and the n state there, and they are completely orthogonal to each other. You can have an initial psi here, and as time passes, this object rotates in Hilbert space. Okay, this object evolves in time here in Hilbert space. That's important. So physical state here in Hilbert space. Okay, let's remember in quantum mechanics, first postulate: a physical system must be described by a state vector, a ket in Hilbert space. What is this? It can be atomic orbitals, or it can be plane waves, or it doesn't matter. It is a complete basis. It satisfies all the mathematical needs, requirements for a Hilbert space. It is complete, it is orthogonal, and you can eventually expand this object there. Well, and this is the first postulate of quantum mechanics. Let's go to the second one. First, let me give you an important example here, which will, I guess, which will make you see the important differences in quantum world and in the classical world of physics. Suppose you are considering electron spin. As a classical sphere, an electron would rotate in an arbitrary velocity, right? It is a classical sphere. So it could rotate here with arbitrary values of speed and in arbitrary direction. Say you represent this by the rule of the right hand rule. So it is rotating here, you assign a spin, an angular momentum here to the classical sphere. So if you project this vector in the, say, the z-axis, you'll find the projection of this vector, which gives you a finite number corresponding to the component S subindex z. Okay, this is an arbitrary value, right? But if you have another direction of rotation, for instance, the sphere would be rotating with the angular momentum x axis, for instance, suppose this is the x axis, you would find, classically speaking, a projection over the z-axis of 0. So if you allow an electron beam, of arbitrary, a bunch of electrons of arbitrary, classically speaking, arbitrary angular momentum, and you measure the angular momentum over z-axis, what do you expect to find out classically? Well, a lot of values from some minimum and a maximum, a continuum spectrum of values. Okay, we'll find that. This is a famous Stern-Gerlach experiment, which was trying to determine the internal degree of freedom of internal, say, rotation of electrons. Classically thinking, okay? But this is classical world. In classical world, an electron would have an arbitrary value and rotate in an arbitrary direction, of course, and you'll find a continuum of possible measurements for the electron spin. So electron spin, the z component of the spin of the electron would be in a set of continuous values. But what do they found experimentally? Of course, all the electrons are conditioned to have a given velocity. It was very well prepared experiment, the Stern-Gerlach, Stern-Gerlach, or perhaps it's pronounced Gerlach, I don't know. But if you can find out a little bit more, just search a little bit about Stern-Gerlach experiment. What they found, two possible values of spin. And this corresponds to, in units of the international system, to h bar over 2 minus h bar over 2. The spots produced, I guess, in a photographic film, I guess. I don't know exactly, now I don't remember exactly what they used to measure this, but they found two spots corresponding to these precise values, h bar over 2 and minus h bar over 2. And this is completely distinct from what one would expect for a classical electron. So in quantum world, you'll find just two possibilities. Also, if you find out an electron with up spin, say they found electrons which have h bar over 2 of angular momentum. They picked apart and inserted again in an experiment, but now to determine the x component. Classically, you would expect 0 because you already have determined it is in the z direction, h bar over 2. Eventually, you would expect 0. But no, they found that electrons, when you measure the z component, also can produce these two possibilities. A little bit more, uh, or a lot more, is discussed elsewhere in the literature. To speak about the first postulate, I will not give a profound discussion of spin here, but what I want to emphasize is this thing. So electrons spin is a quantum object which has only two possibilities: the up state in Hilbert space and the down state in Hilbert space. And these are related to the measurement of the z component of the spin. The operator Sz, this measures the spin of the electron. And electron, the measurement can produce only two values, or spin up in the z-axis or spin down in the z-axis. So electron spin is a quantum object. It is quantum. It is quantized. Say there are two eigenvalues. So the spin matrix Z. We will talk about operators a little bit later, but this corresponds to a matrix like this. And there are two possible states: the up state in Hilbert space, which we can represent this way, and the down state, which we can represent this way in Hilbert space. It is a complete and orthogonal basis for representing the electron spin. But notice an important property here. Suppose uh, ah, it's very important to observe this thing in real world, in real space, where you measure spin. This is the z-axis, and there are two possibilities: or the electron spin points upwards or downwards here, okay? Or it's up. Let me use the green here. Or it's up or it's down. Notice that these two possibilities in the physical world, you are measuring the same axis. They are just anti-parallel. If you are thinking about the sphere rotating, this sphere is rotating this way. Right hand rule this way, points up, rotating here, points up. Or this state points downwards, it's rotating in the opposite direction. Okay? Right hand rule points down. Okay? But they are anti-parallel in real world, in what we see. Okay? This is the z-axis. There are two possibilities. This corresponds to the h bar over 2 for the electron. This corresponds to the minus h bar over 2 for the electron. But in Hilbert space, where things happen in quantum world, you have two, pictorially speaking, okay? Because the components, the amplitudes of a given state may be complex numbers. So in Hilbert space, these two possibilities are orthogonal. In real world, where we measure, they are anti-parallel. But in Hilbert space, they are orthogonal. And that's the space where things matter. Hilbert space. So here is, say, real space. You have here x-axis and y-axis pointing. I don't. Okay, you can find, but there is a z, x, and y-axis, three real axes. But Hilbert space, where dynamics really occur in quantum mechanics, corresponds to just two directions. It is called the basis which diagonalize the spin operator in the z direction. It is a matrix. The spin, the components of the spin, classically, you would speak about the vector, a function s of x, s of y, s of z. It's a function of time, eventually, a function of time. Okay, classically, you could speak about this object. It's a function, function, function. In quantum mechanics, this will be converted to an operator, which is a matrix, a matrix, a matrix, a matrix representation of the components of the vectors. And what can I measure? I can measure only the possible eigenvalues. And so for SZ operator, I have a matrix, SZ matrix, which is 8 bar over 2, 1, and minus 1. I can put the eigenvalues in the diagonal. This is called a diagonal matrix. And corresponding to this eigenvalue, the positive, this possible measurements of the spin in the z direction is this direction in Hilbert space. And this is orthogonal in Hilbert space. This is orthogonal to the possible measurement, or this is orthogonal to the other possible, which is minus 1. Minus 1 is this one. They are anti-parallel in real space. They are orthogonal in Hilbert space. But where I must look for the dynamics, Hilbert space. This is here where things happen in quantum mechanics. So I'm anticipating, I can assume psi here, which is of this form, 1 over square root 2 up plus down. This is the eigenstate of up spin relative or related to the x-axis, okay? But this is, notice, this is a vector, a state vector in Hilbert space. It has components, equal components, in my example, of 1 divided by the square root of 2, right? This is an arbitrary state, an initial state, you can say, right? This is a superposition of up and down states. What are these up and down states? The states of spin for a z measurement. You're measuring the z component of the spin. And you can find just two possibilities, up and down. And these two possibilities are orthogonal in Hilbert space. All right? And you can find linear. You can produce a physical state for your system. In this case, it is the electron spin, which is a quantum superposition. Okay? And in this case, notice that this superposition is not perpendicular to either the up spin in z direction or down spin. But anticipating a little bit, this state vector, corresponds to an electron having its spin pointing in the positive sense of the x-axis, which means you are measuring h bar over 2, but measuring the spin in the x-axis. All right? Notice that's very important. The x-axis in real space is perpendicular to the z-axis, but the state, the physical state representing it, when represented in the basis of the z component, is not orthogonal to either up or down states. All right? It's extraordinary. An extraordinary example of quantum mechanics. The spin system, this is the half spin. It's called spin half. It's a very, very quantum mechanical system. It has all the ingredients you need to know about quantum mechanics. Notice, in Hilbert space, the physical state is neither perpendicular to the up or the down states relative to a measurement in the z-axis. But I am anticipating something. It is the representation of the spin in the x-axis. And in real space, they are orthogonal. X and z, they are two orthogonal axes. But this state, which is the spin up relative to the z-axis, and this state, which is the h bar over 2 possibility of measurement relative to the x-axis, they are orthogonal in real space, but they are not orthogonal in Hilbert space. Notice, this is the physical state psi, and this is the physical state up. They form here. Don't take it too much seriously because or it's a pictorial representation, but here in this case where I can put just real numbers to 45 degrees, but in reality in quantum mechanics these are the components can be complex numbers. I would specify another number here, an imaginary unit here, so it doesn't make much sense to talk about an angle here, okay? So this is an exaggeration here, but it's very important. Things which in real world are orthogonal, vectors which are orthogonal in real world, in Hilbert space may be represented by non-orthogonal states. And things which are non-orthogonal in real space can be orthogonal in Hilbert space. And in quantum mechanics, I must emphasize that in quantum mechanics, it is this object which specifies the system, and the psi, if you project it to the space basis, it's called usually the wave function. It is this object which we need to look at for finding the dynamics. That's very important. Okay, so I guess that's enough for the first postulate of quantum mechanics. The second one, it's a very important, also a very important statement of quantum mechanics. Well, the order of the postulates you can change. There are no a particular order. Second postulate, very important. Physical observables. Okay, it's related to physical observables. A third postulate, I guess I'll talk about the probabilistic interpretation as a third postulate. But in some versions of quantum mechanics, you don't need the probabilistic interpretation. But the probabilistic interpretation is the common ground for everyone working on quantum mechanics, and besides that, another interpretations are very, very non accepted over, not totally accepted. So the accepted theory is the probabilistic one. It's very easy to understand. So we will focus on the probabilistic interpretation, not other possible interpretations of quantum mechanics. And in terms of probabilistic interpretation, you must say that the vector in Hilbert space has a norm, well-defined norm, okay? But We'll talk about the probabilistic interpretation a little bit later. So, this second postulate, physical observables. The physical observable is everything you can measure. So, it corresponds to position, momentum, energy, what else? Electric charge, spin, let's call it S, angular momentum, orbital, okay? This L is usually corresponds to the orbital degrees of freedom for the angular momentum. And what else? If you are talking about fields, maybe electric fields and magnetic fields and what else you can think, all right? Physical observables in quantum mechanics, physical observables must be represented by a very important kind of matrices or operators. If you are talking about differential operators, must be represented by Hermitian operators. Operators interpret as matrices for now. For now, interpret as matrices, but it can be differential operators also. Okay, they must be Hermitian. They must be represented by Hermitian matrices. All right. All the physical observables must be Hermitian. That's a very important question in quantum mechanics. Why is that? Why is that? You need to think about a very important property of what we measure. What we measure are real quantities. What we measure, so physical observables eventually you're not well acquainted with the jargon of the area, so I must talk a little bit what is the meaning of physical observables. Physical observables is or are what we measure. What we measure. As I talked earlier, position, momentum, electric charge, electric fields, and all that. Okay, so what we can measure corresponds to physical observables, what we can physically observe in the physical world, right? So, in classical physics, you have, for instance, position x, momentum p of x. They are functions of time. Okay. In quantum mechanics, or let's stay in the classical world, still in the classical world. These functions are real numbers. The position of the electron is a given number, and if you can find the phase space for x and p, you don't need complex numbers. A given instant of time, electron has a given momentum and it is in the given position. Say the instant t equals to 0, this is the position of the electron and the momentum of the electron. And they evolve in time. So the electron can produce trajectory in phase space, right? But they are real numbers, all right? In quantum mechanics, what really describes the physical system, or really describes the physical system, is the psi. But I cannot measure this directly. what I measure or what we can measure in physical world are position, momentum, energy. So these things must be replaced by some operators, which I'll put a hat here. Do not confuse between unit vectors. X, an operator. Maybe it's function of time. Well, now we'll see that there are two or more possibilities for representing quantum dynamics. There are the most important versions are Schrodinger's and Heisenberg's. But I can put the time dependence here and say this object is invariant in Hilbert space, or I can put dynamics here and this thing can rotate in Hilbert space, and this object is time independent. In Schrodinger's view, this thing is time independent and this thing can rotate in Hilbert space. But I must replace functions of space, time by operators. What are operators? Operators are matrices. Sorry about my dog. Okay, operators are matrices, and matrices we know what they have. They have eigenvalues and eigenvectors, right? So physical observables must be represented by matrices. Well, what kind of matrices? Those those matrices which have real eigenvalues. So Hermitian matrices say A, or let us call O equal to O dagger, the transpose conjugate here, this dagger, remember, transpose conjugate. Just for an example, suppose this matrix, some sigma y, this is a Pauli matrix, the y component of the Pauli matrices, this one corresponds to the spin y direction, normalized by the sy normalized by the h bar of 2. So it's a spin operator. I am anticipating also, but this is a spin operator. I can measure spin, so I can take the dagger of the matrix, and taking the dagger of the matrix, I must first change columns and rows. So this column will become a row, and this column will become a row. And after that, I need to take a complex conjugation. So I transpose the matrix, and I need to take the complex conjugate. So the complex conjugate of I is minus I. The complex conjugate of minus I is minus minus I, which is plus I. So notice this is equal. Okay? And if this thing applies, this property applies, what does that mean really? Hermitian matrices have real eigenvalues. Okay? That's important. That's important information here. An operator which corresponds to a physical observable is Hermitian because its eigenvalues are real. And okay, it's okay to say that the eigenvalues is what I can measure. So what I can measure, what we can measure in the physical measurement, the answer is when you make measurements, you can find for a single measurement in a quantum world, you can extract from that measurement, a single measurement, you can extract an eigenvalue of the operator being used to measure. Okay, so it must be real. If you measure the energy, suppose your operator here is the Hamiltonian, which corresponds, we'll talk about the Hamiltonian a lot, but suppose you're talking about measuring the energy. The energy is represented by an operator. This operator is the Hamiltonian matrix. Okay, the Hamiltonian. And you will try to measure the energy of a nitrogen atom. What do you expect to find? Well, if you don't know quantum mechanics, you don't know exactly what to expect, but certainly you will not to expect to find a complex number. Energy is real valued. You will not find a complex number. So, if operators represent the physical quantities which we observe, so if they are represented by matrices, these matrices must fundamentally be Hermitian, because hermeticity of a matrix ensures that that matrix has only real eigenvalues. That is an important statement. Okay, operators, physical observables must be Hermitian. That's the lesson here. That's a postulate in quantum mechanics. So, operator, physical observables, okay, operators, Hermitian, you have real eigenvalues, and when you measure, you find in a measurement, find an eigenvalue. And the eigenvalue, as you know, for matrices, corresponds to an eigenvector. And the eigenvector is the state after measurement. After measurement. It's the state vector, is a ket. Okay? So, it's another important related issue here is the collapse of the wave function. Collapse of the state, right? It's not a conclusion that can be drawn from the idea that operators are really Hermitian, but the collapse of the wave function is what is a very problematic issue in quantum mechanics. There are a lot of people trying to resolve that problem, but if you have a state psi, say you have psi, this is a physical state of your system. You don't know this thing, you don't know, and you perform a measurement with an operator, say O. What you'll find? you'll find after the measurement a lambda, an eigenvalue of O, okay? And it corresponds to an eigenvector, which I will use a redundant notation. The vector will be indexed by the eigenvalue it has. So it is probabilistic. You can find any. This is a matrix. Suppose it's, I'll put it in diagonal form. It can be in another form, but suppose it has lambda 1, lambda 2, lambda 3 in some basis. And there are many eigenvalues for this operator. When you perform one measurement, you'll find one of these with a certain probability. Okay? You'll find it with a certain probability. After that, if you measure again the same operator, you'll have 100. Here, at the first measurement, you have a probability P, percentage of probability of finding that eigenvalue. Say lambda 1 here. Lambda 1. We'll have lambda 1, 2, 3. So if you perform a second measurement, the same operator, you will find 100% sure the same eigenvalue. And this is called the collapse of the state. You say that the state, which would be, let me write it again here. It will be a superposition in the basis of that operator O. Suppose lambda alpha, you have coefficients alpha summed over all the alphas, lambda alphas, from 1 to the dimensionality of the Hilbert space. Okay, so this summation, it's a state of superposition. It can be in a famous Schrödinger's cat state, if you consider a two-level system, for instance, but can have dimensionality n. So it's at first a superposition. When you measure O, the operator O, which has a spectrum of operators, corresponds to its eigenvalues, lambda 1, lambda 2, lambda 3, and all that. When you measure this operator, the wave function collapses. It collapses to one of its eigenvalues, or to its eigenvectors. Say lambda 2, it has collapsed. After you measured your system, if your system wasn't previously in an eigenstate, in an eigenvector of O, it will collapse to 1. Any one, lambda 1 or lambda 2, with a given probability. And after that, you can measure and measure and measure and measure again. The same operator. You cannot change your operator. Okay? And you'll have 100% of chance of obtaining that. So your first measurement of a quantum state, which you don't have any previous information, is called a preparation. Suppose here you have electron spin half. Spin half, electrons, for instance, can be protons, can be neutrons, it can be neutrinos, it can be positrons, doesn't matter, electrons. Suppose electrons here, you have, I'm only looking at electrons spin, not other properties like position or momentum. I am just interested in spin. So suppose your state is this one, up plus down. It's a superposition of states. Okay? Right. So you perform a measurement of the spin in the z direction. It's your operator. This operator is like this thing, h bar over 2, 1, 0, 0, minus 1. Okay, if you perform a measurement, you will have 50-50 chance because of this 1 over square root 2 is equal amplitudes, 50-50. The superposition has equal proportions. You could produce any other state. You can put complex numbers here. No matter the numbers, I didn't spoke yet of the probabilistic interpretation, but the modulus of the numbers summed up must be equal to 1 to give the probabilistic interpretation. But here, if you measure the spin in the z direction, suppose 50% chance in a single measurement, 50% chance. Toss the coin, heads or tails. You get heads, okay? First toss the coin, heads, okay? In classical world, if you toss the coin another round, 50-50 chance. But in quantum mechanics, this state has collapsed. So in the second round of measurement, the same as of z, you'll get 100% the upspin. And all the previous information, suppose you don't have access to this previously. When you measure, all this thing is lost. You have loss of information. The wave or the state collapsed to this one. You destroy the states if you perform a measurement. Okay, it's completely invasive, a quantum measurement. But since you measure the spin z and you find out it's up for a single measurement, you now have a certainty of a previous next step. As a next step, you have a certainty that your after measurement state, let's call after here, is up. Now you have 100% certainty that your state is up, spin up. Okay, and this is called a preparation. Preparation of a state. You prepare your state to be up, for instance, in this case. Okay, but you could pick up an hydrogen atom which has a superposition of orbitals. Your hydrogen atom would be in 1s and 2p and whatever, a superposition of orbitals, and you perform an energy measurement. For the first time, you get the fundamental state. Now your hydrogen atom is prepared. It is 100% sure from that moment on that it will be in a 1s state. All right? This is called the preparation. Right? Well, so any physical observable must be represented by a Hermitian matrix, which ensures to you that the matrix will have real eigenvalues. You can demonstrate that. Suppose you have an Hermitian matrix, A is equal to H A dagger. Suppose this is valid. You have a Hermitian matrix. This is Hermitian, okay? And suppose you have this eigenvalue and eigenvector equation. Suppose A operating in a given state A, I will label the eigenvectors of this matrix by the same a letter A and the eigenvalue by A. You could put lambda of A, or simply A multiplying the vector A. It's a notation used in particular in Sakurai, so adopt the Sakurai notation. You could use lambda to represent the eigenvalue corresponding to the A eigenvector, but Sakurai uses a redundant notation. He uses A, this is the number, the eigenvalue, and this is the vector, okay, for indexing, all right? So this is the eigenvalue equation. If you take the complex conjugate of that equation, you'll have A, H dagger here, but it's the same, all right? If you take two matrices, A, B, remember, you need to reverse order and take the complex transposition. So we'll have this equation, which represents numbers are numbers. You can put whatever you want, but let's do it right way. So this is number, complex conjugate of that number, right? And now this is the same A, but look, you have a matrix which has a set of eigenvalues lambda a1, suppose a1, a2, a3, and so on, corresponding to the eigenvectors or kets in the Hilbert space a1, a2, a3, all that. This is a complete basis, which means any vector, any eigenvector of an operator in quantum mechanics is orthogonal to any other eigenvector of that matrix. It is ensured by Hilbert space, the properties of the Hilbert space. So suppose I pick this equation here and I multiply it by a prime, perhaps another, a distinct value, perhaps from A. So I'll have this. It's equal to, this is a number, so a number you can put in front of all that because you are projecting this equation over this A primed vector. Okay, it's a bra vector. It's a bra, all right? Here, from the orthogonality of the basis, you have delta A prime A. This is a delta, a Kronecker delta in the case of a continuous base. Okay, so it's 1 if A prime is equal to A, or 0 if A prime is distinct from A. Okay, it's a Kronecker delta. And here, because of the associativity of matrix algebra, I can operate this to the right, or I can operate this to the left, and I'll operate this to the left, right? I'll operate this matrix to the left, which means I will multiply this row vector by the matrix first, instead of multiplying this matrix by a column vector here first. So if, and we are choosing that to be, if this is an eigenvector of A, by this equation, I know that operating to the left, I will have A prime complex conjugate A prime A here, okay? Because after you apply this here, you'll have the number, which is the eigenvalue. Eigenvalue is just a number which is the A prime complex conjugate A prime multiplied in an inner product by A, and this is also the Kronecker delta, So I can rewrite this equation as in the following way. A prime complex conjugate minus A delta, Kronecker delta, A prime A is equal to 0. And there are two possibilities here. Or A prime is distinct of A, in which case you'll have 0 because this is the orthogonality of the basis. All right? So equation is already solved. If you choose A prime distinct of A, the first eigenvalue and the second eigenvalue, for an example, you'll have 0. And the equation is automatically satisfied. But if you choose the A prime equal to A, this gives 1 here. And to satisfy the equation, this term must be 0. So, for A prime equals this vector equals to this, you must have A prime complex conjugate minus A equals to 0, which means they must be equal. This thing, complex conjugate of A prime, must be this, but A prime is equal to A, so I can drop out the prime here, and I'll have A prime, A complex conjugate is equal to A, and only real numbers satisfy that equation. Suppose A is equal to a real part plus imaginary part. So complex conjugate will have the real part minus I, the imaginary part must be equal to the real plus I imaginary part. Real is equal to real minus the imaginary equals to the imaginary, which means the only possibility is 0. Because if you put any other number here, non-zero number here, you will not be able to satisfy the equation. So Hermitian operators, as a corollary of being Hermitian, have real eigenvalues. Real eigenvalues. Okay? This is important. So, summarizing what we found here, Hermitian matrices have real eigenvalues. Real numbers must be related to what we measure, physically measure. So, the representation of operators in quantum mechanics must be done by Hermitian matrices or operators. If you are talking about differential operators, they must be Hermitian. They must have only real eigenvalues, okay? Because you do not measure imaginary energies or imaginary values for spin or for position or for velocity. You measure real numbers, okay? Well, so far so good, I guess. I don't know. I hope. So, the third, and I'll finish with this last third postulate. Perhaps I've forgotten something, but in the right moment, it will come to us. Third postulate. It is due to Max Born. Probabilistic interpretation. Okay. This will be the last postulate from of the present lecture. Okay. Probabilistic presentation says that the given a physical state psi, okay, state physical states are kets in Hilbert space. This is what Max Born did. The Copenhagen, it's due to Max Born, but the Copenhagen school, which was composed by Heisenberg, Bohr, Max Born, and another name, Pascual Jordan, Dirac. They embraced the probabilistic interpretation. Given a physical state psi, there is a probability of measuring the state phi, another state in psi, and is represented by this thing. Given psi, the probability of measuring phi is equal to the modulus squared of the projection, one state into the other, the modulus squared. Why must be the modulus squared? Because the scalar product in a Hilbert space is a complex number. So you also don't have physical probabilities or probability, which is complex. Probability is a real number. This way, the probability of finding phi given the state psi in a measurement is equal to the projection of one state into the other in Hilbert space, but modulus squared. And I emphasize that it's modulus squared because scalar products in Hilbert space are complex numbers. So you cannot have complex probabilities. You must have real probabilities. Okay, this is bigger or equal, at least equal to 0, and it's less than unity. So or equal to unity if the phi state is equal to psi. Okay, so this state represent amplitudes of probabilities of finding things in real world. A measurement of a physical observable. When you measure spin, you have a probability, right, of a given result. So it's important. If you specify the psi as a summation over psi alphas in a given basis alpha, if you project the psi over itself and you take modulus squared, you must have 1. Why is that? Because what is the probability of measuring psi given psi? It must be 1. It's like you prepared the state. You toss the coin. It gave you a tail, right? Or a head. Okay. After that, you have 100% sure that what that measurement resulted in. So, if you have a physical system represented by a state psi, and you are sure that state represents your physical system, then the probability of finding the state in that state, given that state, is 1. And you find out by modulus squaring that. Notice you can insert here any basis, all right? You can insert. So for a given state, this must be 1. Because, all right, you would think about a complex, but for the definition of a bra and a ket space, it is not possible. You would think, All right, I'll find this complex product to be a phase, just a phase. Okay, it will be because the modulus of a phase is equal to 1. But for the from the definition of a Hilbert space, it must be 1 with phase 0. It's a real number. It's 1. Well, you could find out -1, but it would be odd to find that. It's a non-metric space, all right? You are We are talking about a Hilbert well-behaved Hilbert Norman space. So we'll find we'll impose this condition, because if the modulus square is equal to 1, the projection of the state over itself must be 1. So vectors in quantum mechanics, in a Hilbert space, vectors are normalized to unity because of the probabilistic interpretation. So you can do the math and you'll find out, do for yourself the same, but you'll find out the summation of the modulus squared of the numbers here over the entire set of states from 1 to n must be equal to 1. This is because of the probabilistic interpretation. And if you are dealing with a continuous space, for instance, you can consider expanding the wave function or the state, the ket state, in the position basis. So psi projected to psi is equal to 1. And if you insert the unity here, and you resolve the unity, the identity matrix, give me your pardon because I don't know if I said anything wrong here. You can insert it here, position basis. It can be a vector, position vector here. This will be a three-dimensional integral over x, y, and z. So this is x, y, and z, x, y, and z. Doesn't matter. But I'll just be using only one dimension here. It's easy to see now. And this thing is just the psi of x. Psi of x. When you put the integration symbol here in front of all, you project psi over x, you get the complex conjugate of the other product, and this is the modulus squared. So you have an integral over x, modulus squared of x, and this is the probability. Now it's a probability distribution. It's a density, a probability density for a continuous Hilbert space, all right? And you would be doing, for example, you would be calculating the probability of finding a given state phi, or if you have a physical state psi, what is the probability of finding another state phi? You would insert the identity here, resolving any basis you want. You'll find out in a continuous Hilbert space a phi complex conjugate here, multiplying psi, and this will give you the modulus square of that integral. You'll have the probability of finding that. Given psi, probability of collapsing to phi is equal to the modulus square of that integral. Psi of x, right? Modulus squared, right? You can find out that. Well, and this is a very important result. Summarizing what you've done here. physical systems are represented by a ket in Hilbert space. Physical observables are represented by Hermitian operators because real eigenvalues. Right? Physical observables like energy, momentum, position, and all that, right? And probabilistic interpretation. So it must be the case that you normalize the states. Modulo squared is equal to 1. Right? That is the summary of the postulates we talked in this lecture. Right? In the next one, we'll talk about more about the postulates of quantum mechanics. I hope you enjoyed, and bye bye.